right, so the fourth skill that's important to think about from chapter 16 is some theoretical stuff, thinking about collision theory and transition state theory. So again, collision theory talks about the importance of atoms, molecules, or ions colliding to react, and we can think about that qualitatively to kind of explain the effect of concentration and temperature on rates. But quantitatively, we can think about using this equation. And again, this Arrhenius equation will allow us to relate the temperature dependence of rate constants as a way of determining the activation energy of a process. And so that's basically what sample problem 16.8 is determining the energy of activation. And I reminded you in class, and we'll see one more version of this, this equation should look similar. It looks very similar to when we related pressure and temperature to think about delta H of vaporization when we use the Clausius-Clapeyron equation. So again, this is a way that allows us to use this form of this equation, relating the temperature dependence of the rate constant so that we can get from the slope and the y-intercept meaningful values. And again, we're going to get from the slope the activation energy here when we plot this. So, but we're not plotting this here. We're actually just going to use this equation and solve for, in this case, the activation energy. So they tell us here that the decomposition of hydrogen iodide, they give us an equation here, has rate constants of 9.51 times 10 to the minus 9th liter per mole seconds at 500 K and 1.1 at times 10 to the minus 5 liter per mole seconds at 600 K. So find E sub A. And one of the things that's going to become challenging as we continue to move through Gen Chem 2 is realizing, we keep building and having more equations and more different ways that we can think about solving problems. So one of the skills that might be helpful to start working on is every time you work on a problem, ask yourself, after you've done it, how would I know to go back and kind of know to use the kind of equation that I did, or how to solve the problem in the way that I did? And so that's why I always like to start a problem by kind of writing out, taking away from kind of the sentences and words, write a list of the information that's given. And sometimes that can help sort out how you need to solve the problem. So in this case, they give us two different rate constants, and I'm going to call K1 here 9.51 times 10 to the minus 9th liter per mole second. So that rate constant is specific to this temperature, which is 500 K. The second rate constant is 1.1 times 10 to the minus 5th liter per mole second, and again at a higher temperature, 600 K. We know that R is 8.314 joules per mole Kelvin. One of the things, again, I commented in class that I noticed on the last exam is you have to make sure that you're using the correct R value. In this case, we don't want to use the 0.08206 liters per mole atmosphere. That's not going to give us units that's going to allow us to get the right answer here. We want an activation energy, which is going to be in units of joules per mole or kilojoules per mole. So we need to have an R value that's going to allow us to incorporate that. Okay, so looking at this problem, again, we've got two rate constants, two temperatures, and R value. You'll always be given equations. It should jump out at you, hey, here's what I want to solve, activation energy, and I'm given the rest of the parameters. So that's the equation that I want to use. So again, the natural log of rate constant at temperature 2 over rate constant at temperature 1 equals minus EA over R times 1 over T2 minus 1 over T1. And as we talked about with the Clausius-Clapeyron equation, a common mistake that students make with these problems is not correlating the correct rate constant with the temperature. So that's why I listed these here with K1 and K2, T1 and T2, because we have to make sure we pair them in the right spots in the equation. Otherwise, you won't get the correct answer. So the natural log of 1.1 times 10 to the minus 5th liter per mole second over 9.51 times 10 to the minus 9th liter per mole second equals minus E sub A, which is what we're solving for, 8.314 joules per mole Kelvin. And again, our temperatures were already given in Kelvin here, so we don't need to worry about doing any conversions. 1 over 600 K minus 1 over 500 K. And again, I made sure to match my K2 value here with my T2 value here. We want to make sure that we have the right parts in the right part of the equation. So sometimes people are tempted to, hey, I've got an ln term, let me do the e to the. This is just going to be a value. There's nothing that we're solving for here, so we don't need to use e at all here. We just need to take the natural log of whatever this value is, which is 1156.67. No units here because those units of those rate constants are going to cancel, equals minus E sub A, 8.314 joules per mole Kelvin. I'm going to break this part up and get a value for this, minus 3.33 times 10 to the minus 4th reciprocal Kelvin, right? And we can see here, we can start looking at the fact that units are going to cancel. I know it's a little bit hard to see here. This is in the denominator. This is in the denominator of the denominator. So those guys will cancel. Natural log of this term is 7.0533. And you notice that I'm keeping well more than the number of significant figures we'd have for this problem, which is going to be 3, because I don't want to make a rounding error early that's going to give me the incorrect answer. So keep, 5 or 6 significant figures as you work through problems until the end when you can then reconcile. So minus EA, kind of combining these terms, we're going to have minus 4.00529 moles per joule. And I know that looks weird, but keep in mind, this is the unit that we're solving for. So once this term and its units come over on the other side, they'll be flipped, and we'll have the correct units in terms of energy of joules per mole. So finally, E sub A is going to be equal to 176,100 joules per mole. Okay, rounding for the correct number of significant figures. So for 2 significant figures, 1.76 times 10 to the 5th joules per mole. And if you want to, you can go ahead and put that in kilojoules per mole, 1.76 times 10 to the 2nd kilojoules per mole. If you have a value that's large enough to put it into kilojoules per mole and not have it be a decimal value, that's kind of a common thing to do.